so far we've only seen examples where a function is actually equal to its Taylor series. And so it might seem like we're being overly pedantic and worrying about whether or not a function is equal to its Taylor series or not. Unfortunately, it turns out that there are some relatively simple functions whose Taylor series are not equal to the function. And so here is an example of a function like this here. So let's consider f of x, which is defined as a piecewise function where it's 0 when x is equal to 0, and it's e to the minus 1 over x squared when x is not equal to 0. And now I want to find the Taylor series for this function centered at 0, or in other words, the Maclaurin series. And so it'll help first just to visualize this by drawing a graph of the function. And so here I have the x-axis and f of x. And I want to figure out what happens as x gets very large or very small, just so that I can draw a rough sketch of this function. And so first of all, when x is very large, then if I look at this power right here, then the e to the minus 1 over x squared, the minus 1 over x squared goes to 0. And so that would mean that e to that is going to 1 overall. And so that tells me that in both the very positive direction and the very negative direction, I'm going to have a horizontal asymptote near x equals 1. Then I want to figure out what happens near 0. First of all, I know that the function is defined to be 0 at 0, but at this point I don't necessarily know that it actually approaches 0 nearby. But if I consider e to the minus 1 over x squared near x is equal to 0, first of all, the 1 over x squared explodes near 0. And in other words, I mean that it's very, very large. And so if I'm putting a negative sign out in front of that, it's going to be very, very negative. And if I take e to that, then it's going to be very, very small, because it's going to be e to a very large negative power. And so that means that my function will be really close to 0 near 0. And so if I sort of connect the dots here, then I'm going to get something that looks like this. And it turns out that actually, if you draw this a little more precisely, the function is really, really flat near x equals 0. And the reason why that's important is because you could compute the derivatives of this function. And because it's a piecewise function, it ends up being a little bit annoying, and you would have to do some careful limit tracking here of functions as they approach 0. But it turns out, in particular, that the nth derivative, so fn, evaluated at 0 is equal to 0 for all n. And so you could verify that by trying to take some of these derivatives yourself if you want. But that tells you that the Taylor series for f of x is just equal to 0 because all of the derivatives are 0. And so when I plug that into the typical formula that we have, we just get 0. And so that means that the Taylor series converges for all x. So this series is converging to a particular number regardless of what x you plug in, which of course in this case is just 0, but it's only equal to my original function at x equals 0. And so the point here overall then is that this function has a very nice behaved Taylor series because it's just the series of all zeros. And so that converges everywhere, it's well behaved, but it's just not equal to the function at all, except for at one point. And so that means that we have to be careful when we're computing Taylor series, because they may or may not actually represent the function that we care about. And so we should spend a second worrying about what the problem was for this function. And it turns out that if you take the derivatives of this function, they grow very quickly in comparison to the original function. And so that means that the error bound in Taylor's remainder theorem isn't really very helpful here because the errors are so large. And so in particular, the errors are larger than the function would be itself, or actually they're really just equal to the function itself. And so that means that the Taylor polynomials don't do a good job in this case of estimating the original function.